In the past 2 weeks, we have introduced the ordinary differential equations and numerical methods for solving them. And this week, we're going to talk about partial differential equations. In particular, we're going to talk about 4 topics today. First, we're going to give a brief introduction about the definitions of partial differential equations and make some connections to terms we learned in the ordinary differential equation case, such as order, linearity, etc. Secondly, we're going to talk about different types of partial differential equations and how to classify them into elliptic, hyperbolic, and parabolic differential equations. Thirdly, we're going to introduce some famous and very well-known partial differential equations, which we actually encounter every day in our physical world. We'll provide some physics intuition and hopefully convince you that partial differential equations may be one of the best ways of describing the fundamental physical laws in this world. And in the end, we're going to talk about boundary conditions that commonly appear in partial differential equations. Before we jump into the 4 topics, let us first see a cool simulation of turbulent flow that pass through aircraft. So this work is done using the computational fluid dynamics programs, which solves the NaviStokes equation numerically. This equation is maybe one of the most famous equations and maybe difficult to solve equations that are most difficult to solve in today. The computational fluid dynamics programs that solve the NaviStokes equations for simple and more complex geometries have become an integral part of modern aircraft design. The CFD, or computational fluid dynamics techniques that solve these equations, have helped, for example, to improve flight stability and reduce drag in modern aircraft. Though, in fact, physical wind tunnel experiments are currently indispensable for validating the results of the CFD analysis, the combined effort of CFD and wind tunnel tests are still critical in the development of, for example, supersonic aircraft. And this Navier-Stokes equation is just a typical example of how our quest to understand nature has provided engineers with a powerful new tool to design improved technologies to dramatically improve our quality of life. So let us now talk about the definitions of partial differential equations. So these equations involve partial derivatives. So it has several independent variables. In the left-hand side, we have the partial derivative of uxt with respect to t. Maybe so t may represent time. And in the right-hand side, we have partial derivative with respect to x. And here is second partial derivative with respect to x. So it has more than one independent variable. And for ordinary differential equations, we only have one independent variable, and here we only have, for example, the time t here. So in some way, you can view that partial differential equation, and in particular for this example, as an infinite number of ordinary differential equations. Right? For every x, you have a derivative with respect to t. Just intuitively speaking. And you can see or imagine why, in general, partial differential equations are harder to solve than ordinary differential equations. And the terms like linearity and water are similar as in the definition of ordinary differential equations. So linear corresponds to whether the equation is linear with respect to the dependent variable, and in this example is u here. So we know taking derivative is a linear operation, right? So we only have partial u, partial t. We don't have partial u squared or partial sine of u. And in the right hand side, the same. We have second derivatives with respect to u. So you can check that, in fact, this partial differential equation, which is called actually heat equation or diffusion equation, is a linear partial differential equation. We'll come back to this equation later. So the linearity is with respect to linearity in the dependent variable, which is u here. And the order of a differential equation is the order of the highest derivative in the differential equation, which is same as in the definition of ordinary differential equation. And in particular, we have a second order partial differential equation here. Okay, so also in practice we use abbreviations or shorthand notations. So since we have more than one independent variables, sometimes we write, for example, here we have u subscript t to denote the partial derivative of u with respect to t. And if we have uxx, it simply means second partial derivative with respect to x, second order partial derivative. And you get the gist of it, right? So now we can talk about different types of partial differential equations. And the intuition is in the definition of equations of conic sections. We know that a quadratic equation, the solution of quadratic equation represents a conic section, right? It's a curve in a plane. And in particular, you may have seen that if in this equation b squared minus ac equals 0, it describes a parabola, and we'll say this is a parabolic curve. And if b squared minus ac is positive, it describes a hyperbola. We'll say it's hyperbolic curve. And if b squared minus ac is negative, we'll say that this equation describes a elliptic curve. And similarly, we can define the so-called parabolic partial differential equation, hyperbolic partial differential equation, and elliptic partial differential equation. Here we don't have x squared, xy, y squared, etc. Instead, we have derivatives uxx, uxy, uyy, right? So these are second derivatives. And so if we write a general partial differential equation in this general form, if, for example, b squared minus ac is 0, we say this partial differential equation is a parabolic equation. And here's an example. So we have ut equals d squared times uxx, and this is called the heat equation, which we'll also talk about later. But for now, let's just look at the formula here. Here we don't have x and y, and imagine that t is a variable y here. So we don't have mixed terms, so b is 0 in this case, and we also do not have utt, so c is 0. And if b and c are 0, then b squared minus ac is equal to 0. So this is a parabolic equation. As a second example, let us look at this 1D wave equation. We have UTT, but T usually denote time, equals c squared times uxx. So again, we are writing this equation with variable t and x instead of xy. It's just different names of variables, so that doesn't really matter. So imagine that we have this equation and t replace the role of y here. We still do not have mixed terms uxy, so b is 0 here. And if we make every term in one side, we actually will see that a and c, a is the c squared here, and c is actually -1 if we move everything to the right hand side. So in particular, we have b is 0, and a and c have different signs. So eventually we have b squared minus ac being positive. So the wave equation is a hyperbolic equation. And here is an example of elliptic equation, which is more often called the Laplace's equation. In particular, let us just look at the coefficients. So here a and c both equal to 1, and there are no mixed terms, so b is 0. And in particular, we have b squared minus ac equals -1, so this equation is elliptic. So in this class, we're just going to give you these definitions, and maybe when you read in articles, you know what they mean by elliptic, hyperbolic, or parabolic. But we're really not going to do anything with this classification in this course.